In this video, I'm going to show you a set of axioms for geometry that work very well for Euclidean geometry and also work nicely for two other of the 9 Cayley-Klein plane geometries, the two in which parallel lines are unique, that is Galilean geometry and Minkowskian geometry. And I would say that for current day mathematics, this is the preferred way of introducing axioms for Euclidean geometry. I'm going to start with axioms for a two-dimensional vector space. You've very likely met vectors in a physics course, if not in a math course. You may not have seen these axioms before, but they're very similar to the axioms for a field. So the first axiom is that there is a zero vector, which functions as an additive identity. When you add it on to any vector v, you get back the vector v that you started with. Similarly, there's an additive inverse axiom. For any vector v in the vector space, there's a vector denoted by minus v, with the property that when you add v to minus v, that's equal to 0. The third axiom is that vector addition is commutative. This is in fact not an independent axiom. I can prove it from the other axioms, and I can prove it from the other axioms even if I don't assume that the additive identity and the additive inverse work on either side. The fourth axiom is that vector addition is associative. The fifth axiom, the one of these that you might overlook if you were trying to write out the axioms from scratch, is that the multiplicative identity in the real numbers is also a multiplicative identity for vectors. That is, if you multiply any vector by 1, you get back the same vector that you started with. Next, we have another associative law for scalar multiplication. If we take a vector, multiply it by b, and then multiply the result by a, we get the same answer as if we had first multiplied a and b together and then used their product to multiply v. Well, we've got another page of axioms. Here they are. We need two distributive laws. One that says scalar addition is distributive. If you add a and b together and multiply the result by v, you get the same vector as if you had multiplied a and b separately by v and added those vectors together. And we also need a similar distributive law for vector addition. When you multiply a by the product of two vectors, you get the same answer as if you'd multiplied a by each of those two vectors separately and added the results together. Those 8 axioms are the axioms for an abstract vector space over the real numbers in general. For a two-dimensional vector space, I need two other very important axioms. One says that the dimension of the space is greater than 1, and the axiom states that there exist two vectors that are linearly independent. By linearly independent, I mean the only way you can make the zero vector by adding a multiple of a to a multiple of b is by choosing a equals b equals 0. If you think of vectors as arrows drawn in a plane, this simply means there are two vectors that point in different directions. They're not all along the same line. Finally, we need an axiom that states that the dimension is also less than 3, and that axiom states that given any three vectors u, v, and w, they are linearly dependent. By linearly dependent, I mean that I can choose coefficients a, b, and c such that au plus bv plus cw equals 0, and I can do this in a non-trivial way, other than by just setting a, b, and c all equal to 0. Since the dimension is less than 3 and greater than 1, that means it's equal to 2. And the simplest model for this set of axioms is R2. The vectors are just pairs of real numbers. We add them component by component, and if we multiply a vector by a scalar a, that just means we multiply the two components by a. Well, we don't have geometry yet because we don't have points. So in order to introduce points into this axiom system, I'm going to state two additional axioms. And the place I learned about these was in a lovely little paperback written by the great Russian mathematician Yaglam for high school students in Moscow. Yaglam's first point vector axiom says that 2 points determine a vector. Or to be precise, if you give me a point A and a vector V, I can do what everyone calls adding the vector V to the point A. And when I do that, I get a unique point B. So what the axiom actually states is you give me a point A and a vector V. There is one and only one point with the property that the points A and B determine that vector V. And everyone calls that the vector from A to B. The second axiom says the first axiom has to be consistent with the concept of vector addition. And I'm going to try drawing a little diagram for this. So I will switch over to drawing arrows. And I'll draw an arrow from A to B. And then I'll draw an arrow from B to C. And let's see if I can make text labeling work in this little tool. One of these things must be a text tool. Here it is. There's A. There's B. Whoops, I don't want you there, C. There's C. Now A has disappeared. Okay, so what the axiom says is if A and B determine vector V in accordance with the first axiom, and B and C determine vector W in accordance with the first axiom, then if I ask what vector is determined by A and C, the answer is it's the vector V plus W. This is usually the way vector addition is introduced in physics courses. But if we want to introduce points axiomatically, we need this in order to make our point vector relationship consistent with the rule we already have for adding vectors. Finally, we need to define a line. A line is specified by a point and a direction vector. You're already familiar with that idea. You've seen it in several geometries. And a point B is on the line that's thus specified if and only if, when I take the points A and B and in accordance with the first axiom, ask what vector takes me from A to B, the answer is it's a vector that's a multiple of the direction vector V. A simpler way of stating this is the line is the set of all points obtained by taking the point A and adding on some real multiple of the vector V. The points and vectors of R2 satisfy all these axioms. And if you're going to distinguish points from vectors, it's very useful to denote a point of R2 by putting it in ordinary parentheses, while a vector is denoted by using square brackets. You can add a vector to a point and get another point. You can add two vectors and get another vector. But in general, points cannot be added to one another. Now, once you have these axioms, it turns out that there is an intimate connection between parallelograms and vectors. Here are some theorems. I'm going to ask you to prove a couple of these on the homework that explain what can be proved in terms of this relationship. First, suppose you've got two lines, L and L prime, and their direction vectors are proportional. In that case, they're either the same line, they have all points in common, or they are parallel. So the idea of proportional direction vectors implements the basic idea of Euclid's fifth postulate. The converse of this result is also true and easy to prove. If you have two parallel lines, in the sense that they don't meet, then their direction vectors have to be proportional. And finally, if you draw a parallelogram, the opposite sides of a parallelogram are equal vectors. This is in fact proved in Euclid. It's Book 1, Proposition 34. Now we have a way of adding vectors without using coordinates. Doing this is kind of like ordinary Euclidean constructions, except that instead of using a straight edge and a compass, we're using a straight edge and a parallel ruler. A parallel ruler is a device in which a couple of straight edges are joined together by rods with movable joints in such a way that the rulers always remain parallel. And we need two operations. The first one, in accordance with Euclid's first postulate, says we can, with our straight edge, draw the unique line that passes through two distinct points. With our parallel ruler, what we do is lay down the line lay down a point that's not on the line. How am I supposed to get a point? Well, I'll use a pen to draw a little point. Okay, there's a little point, and with the aid of my parallel ruler, I can now construct the unique line through that point that's parallel to the first line. So I now want to show you how I can accomplish vector addition with the aid of these two drawing implements. I want to add the vector AB to the vector CD, and there's one especially easy case, the one where the head of AB is the same point as the tail of CD. In this case, the axiom that I've already stated does the job. It says if I simply draw the vector from A to D, that is the vector sum V plus W. The next case is a little bit trickier. I have moved the vector CD so that its tail doesn't coincide with point B, but since opposite sides of a parallelogram are equal vectors, all I do is construct a parallelogram where this side goes from B to C, this side is parallel to it, this side is parallel to AB, and then AB and A prime B prime are equal vectors, so adding A prime B prime to CD does what I want. I simply draw the vector that goes from A prime to D, and there is my vector sum. The trickiest case is one you might have thought would be the easiest case. It's the case where AB and CD happen to lie on the same line. And in this case, we have to draw two parallelograms. We draw one parallelogram that creates a vector that's equal to AB anywhere that's not on the line. The length of this side is irrelevant. Any length works equally well. And then I draw a second parallelogram which creates a vector that is equal in length to that vector and that vector, but that conveniently is drawn adjacent to CD. So now I have CD added to a copy of AB, and the resulting vector sum just goes from C to E. Well, we got points, we got lines, we still don't have length and angle, but those are quite easy to introduce by introducing a dot product into our vector space. Our axioms so far have defined what's technically called two-dimensional affine geometry. In affine geometry, there is no concept of length or angle, and therefore an arbitrary stretching of the plane along any axis is still something that will preserve the truth of all theorems of the geometry. If you don't set ASP equals 1 in your R script, you're working in affine geometry, and you've met a few theorems of affine geometry. A lovely example is the theorem of Menelaus. But if we want to go beyond affine geometry and introduce the concept of length, we need a dot product, and it has to satisfy these axioms. First, it's symmetric. You take the dot product of vectors v and w in either order. The answer is the same in both cases. Second, it obeys a distributive law. Third, it is positive semi-definite, by which I mean that no vector has negative squared length. And finally, the only vector with zero length is the zero vector. If you eliminate axiom 4 and replace it by an axiom that says there are vectors of zero length that are not the zero vector, but they're all proportional to one another, then you end up with Galilean geometry. It's a lovely geometry, but we don't have time to do it in this course. My apologies. If I throw out axiom 3, as you'll see shortly, we end up with Minkowskian geometry rather than Euclidean geometry. So now we've got length. I simply define the length of a vector to be the square root of the dot product with itself. If I want to introduce angle, I use the property with which you're already familiar, namely the dot product of two vectors is the product of their lengths times the cosine of the angle between them. So I say, given two vectors v and w, the angle between them is just the arc cos of their dot product over the product of their lengths. With this definition of length and this definition of angle, I can now develop all of trigonometry. And I'm going to content myself with proving the law of sines and the law of cosines in Euclidean geometry. So let's start with the law of cosines. We've got a vector A that goes from vertex C to vertex B. We have a vector B that goes from vector C, point C to point A, and the vector difference between those two vectors, C, is a vector that goes from B to A. It's the third side of the triangle. Now I take the equation C equals B minus A, square both sides, and on the right, of course, squaring means I take the dot product of the vector B minus A with itself. I get B squared minus 2B dot A plus A squared. If I write that out in terms of lengths and angles, I get A squared plus B squared minus 2AB cosine C. So this is one way of stating the law of cosines. You can view it as sort of a correction term on the Pythagorean theorem. If cosine C is not 0 because angle C is not a right angle, then C squared is A squared plus B squared minus an additional term that involves the cosine of the angle between vectors A and B. A more interesting way of writing this is by solving it for the cosine of C. The cosine of C then turns out to be A squared plus B squared minus C squared divided by 2AB. And this formula is interesting because it lets us write the cosine of any angle of the triangle in terms of the lengths of the three sides. You've already seen in Euclidean geometry that given three lengths that satisfy the triangle inequality, I can construct a triangle with those three lengths, and therefore it shouldn't be unreasonable to discover that the cosines of the various angles are completely determined by the lengths. Next, I want to derive the law of sines. There are lots of short derivations of the law of sines. I'm going to use one that is not short. In fact, it's quite messy, and I'm not going to do the algebra out. I'm just going to tell you the result. I can write sine squared of C as 1 minus cosine squared C. On the previous slide, I have a messy expression for cosine C in terms of side lengths A, B, and C. And if I compute sine squared C over C squared by just plugging in the law of cosines for cosine C and collect terms in a clever way, I discover that sine squared C over C squared is twice A squared B squared plus A squared C squared plus B squared C squared, which involves A, B, and C in a thoroughly symmetrical way, minus A to the fourth plus B to the fourth plus C to the fourth, which involves A, B, and C in a symmetrical way, divided by 4A squared B squared C squared. So since this expression involves A, B, and C in a thoroughly symmetrical way, I clearly would have got the same result if I'd set about to calculate sine squared A over little a squared or sine squared little b, capital B over little b squared, and therefore sine capital C over little c has to equal both sine capital A over little a and sine capital B over little b. That's the law of sines. If you want to check one special case of this, consider an equilateral triangle whose sides are all of length 1. In that case, the first term here is going to be 2 times 1 plus 1 plus 1, which is 6. The second term is going to be 3, and 6 times 3 divided by 4 is equal to 2 over 4, which is equal to a half, which is indeed equal to the cosine of the 60-degree angles in an equilateral triangle. Now I'm going to drop the third postulate and come up with Minkowskian geometry. In Minkowskian geometry, a point of the geometry represents an event in space-time. The first coordinate, written on top, is the time at which the event occurs, and I can specify it either in years or in nanoseconds. The second coordinate is the location along a single straight line at which the event happens. Again, I specify the position either in light years or in feet. Clearly, if I specify time in years and distance of light in light years, by the definition of a light year, the speed of light is 1 light year per year. It's a happy numerical accident that if we measure distances in feet and time in nanoseconds, units of 10 to the minus ninth seconds, the speed of light is almost precisely 1 foot per nanosecond. The people who defined the foot and the second did not know this. It's just blind luck. A line of Minkowskian geometry represents uniform motion. If you're using years and light years, think of it as motion of some interstellar spaceship. If you're using feet and nanoseconds, think of it as being the track of a subatomic particle. Nothing can go faster than light, so the slope of one of these lines, if I plot it in a plane where I plot space coordinates vertically and time coordinates horizontally, then the slope has to be between -1 and 1. That means that the direction vector for a line has to be a vector for which the square of the time coordinate minus the square of the space coordinate equals 0. Notice in Minkowskian geometry, I change a sign in my definition of the dot product. You've already seen this done before in hyperbolic geometry. And once I do this, the third postulate about the inner product is no longer valid. Instead, it's been replaced by a postulate that says there exists a vector with positive squared length, and there also exists a vector with negative squared length. Such a vector is called time-like because you can pick a frame of reference in which the space separation of the two events is 0. That would be a frame of reference moving on the spaceship we had in mind. And in that case, the length of the vector turns out to be the elapsed time on a clock on board the spaceship. That's a remarkable physical result. There are also space-like vectors where the dot product of the vector with itself is less than 0. Those are perfectly valid vectors, but such a vector cannot be a direction vector for a line because in Minkowskian geometry, a line corresponds to physically possible motion. There are also light-like vectors whose length is 0. This describes the motion of a massless particle like a photon. These lines, however, are not lines of Minkowskian geometry, even though light-like vectors are perfectly valid vectors. Now how am I going to introduce angles? Well, I can give a criterion for a time-like vector to be orthogonal to a space-like vector. That's the only circumstance under which the dot product of two vectors can be 0. One of them has to be space-like. But there are no right angles between lines of the geometry because the dot product of two time-like vectors can never be 0. If I want to know the angle between two intersecting time-like lines, I take the angles between their direction vectors, and the convention is that the direction vectors always go forward in time. These direction vectors are time-like vectors, being direction vectors, they're unit vectors, and since they go forward in time, they have positive first components. That means when I take the dot product of these two vectors, I'm going to get the product of two large positive first components minus the product of two smaller second components. And it turns out that the dot product in this case is always greater than or equal to 1. That's great for our purposes because we know that hyperbolic cosines always come out greater than or equal to 1. And so I can define the angle in Minkowskian geometry between lines with direction vectors v and w as the inverse hyperbolic cosine of the angle between them. If I do that, it turns out that the hyperbolic tangent of the angle between them is equal to the relative velocity of the objects that were moving with direction vectors specified by v and w respectively. It's the velocity of one of those objects in a frame of reference where the other is at rest. And the same thing actually happens in Euclidean geometry. If I take two lines of Euclidean geometry and rotate the diagram showing the two lines so that one of them is horizontal, then the tangent of the angle between them is the slope of the other line. And now I can state and prove the law of cosines for a Minkowskian triangle. Here is a Minkowskian triangle, and you want to think of it physically. Here is a slow-moving spaceship taking you on a journey that takes a long time to cover a short distance, the vertical distance between point B and point A. And if you do that, and you travel on that spaceship, the ship's clocks advance by 1.69 years during your journey. However, you could make the trip in a rather strange way by first hopping a spaceship that takes you backwards to the left in space for a while. It gets you to event C, and now you really got to get a move on in order to reach event A. If you do that, you discover the ship's clocks on the first ship advance by 0.85 years. Those on the second ship advance by 0.62 years. And 0.85 plus 0.62 is 1.47. Initially, this seems very strange, but in fact, it's valid physics. In Minkowskian geometry, a straight line is the longest distance between 2 points, in the sense that if you're going to travel from event B to event C, the greatest time will elapse if you make that journey traveling at a constant speed. If you make it in different legs with different speeds, the total elapsed time becomes smaller. Now, let's introduce vectors. Vector A goes from B to C, vector B goes from C to A, and the vector sum, which I'll call C, goes from B to A. I use the distributive law just as before, and I get C squared equals A squared plus B squared plus, in this case, 2AB times the hyperbolic cosine of C. If I solve this equation for the hyperbolic cosine of C, I have a formula for the hyperbolic cosine of a Minkowskian angle in terms of the lengths C, A, and B of the three sides of the Minkowskian triangle. Now, how are we going to get the law of sines? Same way we did it in Euclidean geometry. I'll exploit the fact that sinh squared C is equal to cos squared C minus 1 on the previous slide is a messy expression for cos squared C in terms of A, B, and C. If I write it all out, I discover that the formula for sinh squared big C over little c in terms of the side lengths of the triangle involves A, B, and C in a thoroughly symmetric way. Therefore, I would have got the same thing if I'd started with angle A and side little a, or with angle B and sine little b, and it follows that the ratio of the absolute value of the sine of any angle of a Minkowskian triangle divided by the length of the opposite side is the same 3, same for all 3 pairs of angles and sides in the triangle. So there's a quick introduction to Minkowskian geometry. We will return to this topic and introduce the topic of circles in a couple of weeks.